Hi, my name's Jordan Wick,
And I'm Katie Lechtenberg.
and our Science Expo experiment was optimizing coil gun efficiency. So, what exactly is a coil gun in the first place? Well, a coil gun is a device which propels an object using an electromagnet. And the way this works is a capacitor sends a really big pulse of electricity through an electromagnet, which creates a really big magnetic field inside that electromagnet. And that electromagnetic field attracts a steel projectile with a really large force for a really short period of time. And ideally, once the projectile reaches the center of the coil, the electromagnet should be turned off due to lack of energy. And then that way, the projectile can just continue with its current velocity out the other end of the barrel. And so you can kind of see how that works in the graphic shown below. The graphic shown below is what's called a multi-stage coil gun because it has multiple coils placed along the barrel. So that way, the projectile is constantly sped up as it goes throughout the barrel. So, why are coil guns even important in the first place? Well, one of the reasons is because the military has been trying to develop a coil gun mortar due to it not making any sound when it's fired and also its increased accuracy compared to normal mortars. And another use for coil guns has been to send objects into space, mainly small satellites, so that way we wouldn't have to use a rocket every time we wanted to send one up into atmosphere. And then coil guns are usually pretty inefficient. Many of the ones on the internet are less than 1% efficiency, but with superconductors, we can possibly create one that has 90+% efficiency, which gives us a lot of room to improve. So when you're making a coil gun, there's going to be an ideal position where you should start the projectile out before firing, because if the projectile starts too close to the electromagnet before it fires, then by the time the projectile gets to the middle of the electromagnet, there's going to be some leftover energy in the capacitor bank, meaning that once the projectile passes the middle, the electromagnet is actually going to pull backwards on the projectile, which reduces the efficiency. But if the projectile starts too far from the electromagnet, then there's not going to be as much force acting upon the projectile, which means a lot of the energy is just going to go wasted. So when you're making a coil gun, you have to balance these two factors out to make sure that you're getting the ideal efficiency for your combination of coil thickness and capacitance. And each different combination of coil thickness and capacitance has a different ideal starting position, which means you have to experiment with that to get the right combination. So for our experiment, we tested out 3 different capacitor banks and 3 different coils, which made for a total of 9 different combinations of the two. And for each different combination, we tested out 9 different starting positions and tested out the velocity that each starting position yielded. And from that, we figured out what was the absolute maximum velocity that each coil combination could give us. And each of those shots we calculated the efficiency of. And from all that data, we figured out which coil/capacitor combination gave us the absolute ideal efficiency. And we were just trying to figure out which combo worked the best in total. And so our hypothesis was that the coil with 8 layers using a capacitance of 1,000 microfarads would yield the highest overall efficiency.
So here's all the materials that we used in our experiment. So we used 2 9-volt batteries and an 18-volt drill battery, which has a high enough output current to power our boost converter circuit and charge the capacitors to a high voltage.
So this is our boost converter circuit. What it does is it takes an input from the 18-volt drill battery and one of the 9-volt batteries, and it turns on and off an electromagnet really, really fast to charge up our capacitor bank to 300 volts.
So we have 3 capacitor banks, 500, 1,000, and 1,500 microfarads, and the capacitors were obtained from used disposable cameras. So this is our device we use to measure speed. It uses 2 photo gates and it connects to a microcontroller that connects to our laptop.
So these are the coils that we used in the experiment. They had 5, 8, and 11 layers wrapped around them. And the reason that we used clear plastic tubing for the barrels was because we needed light to be able to shine through them for the photo gates to be used, and also so that we could see the projectile when it was in there so we could measure out the starting position.
So this is the laptop we used, and it has Arduino software downloaded onto it. So this is the multimeter, and it measures the voltage across the capacitor bank.
So this is the projectile that we used. It is a piece of steel that is cut 3/4 of an inch long made out of 3/16 inch in diameter steel rod, and we have 7 marks on it so that we can easily change the starting position relative to the coil.
This is the target that we used to catch our projectile so it didn't fly away.
So we used a lot of different miscellaneous parts in this experiment, mainly to make the firing circuit and connect everything together.
So you also need a workstation, so just any open space to run the experiment. If you like, you can also have a lowly lab assistant. Hilarious.
So to measure the speed of the projectile, we had to make a chronometer, which is a device that measures the speed of a projectile. And what it does is it uses 2 photo gates, which are a set distance apart, and a microcontroller that's connected to the 2 photo gates measure the time that it takes for the projectile to go between the 2 photo gates. And from that data, we can determine the velocity of the projectile.
So this probably looks like a huge mess, but the coil is pointed at the target and everything is hooked up so that the coil gun is ready to fire. And also the cookies are necessary.
This shows a basic sketch of the firing circuit that we used in the project, and it shows how all the components are connected together. So now I'm going to go through the procedure of the experiment. First, you charge up the capacitor bank to above 300 volts. Next, you fire the projectile. Next, you record the velocity for the shot.
Ta-da!
Yep.
Oh, there you go.
After this, you're going to repeat the process for each of the 9 different possible starting positions for the projectile. And then once you're done with this, you're going to repeat that whole process for each of the 9 different coil/capacitance combinations.
So here's all the data that we received in the experiment. In each of the 9 charts to the left, there's a starting position, and we recorded the velocity for each of those starting positions. And we had the Excel file calculate the kinetic energy and the efficiency for each shot. And to the right, you can see that we had the max values for each different combination of coil thickness and capacitance. And over right below that, you can see the combination that yielded the highest efficiency out of all the values. So this is the graph that we got from all of our data points. And as you can see, as we increased the starting position, the efficiencies went up and down in sort of a bell curve shape, which means that there were ideal starting positions for each combination of coil and capacitance. And as you can see, the peaks represent the ideal starting position, and they were different for each combination of coil and capacitance. So, in conclusion, as you saw on the graph on the previous slide, when we plot the starting position versus the efficiency, it created a bell curve shape, which meant that there was an ideal starting position for each different combination. And this ideal starting position was different for each combination, as you saw in the graph. And the combo that gave out the highest overall efficiency was the one with 8 layers and 500 microfarads. And this yielded a 2.21% efficiency, which isn't the greatest efficiency, but this can be increased by adding more coils to make a multi-stage coil gun.
So our sources of error, when the coil gun fires, there's a recoil which causes the coil to slide back a little bit, which takes some of the energy. There's an error in starting position because the marks on the projectile are a little bit thick, so there's room for change in the position there. When the coils are fired, they heat up, and that can change the resistance, which changes the strength of the magnetic field. And the capacitors we used weren't very high quality, so the actual values might have been a little bit different from what we thought they were.